Okay, so we are going to start here with our very last set of notes for the semester. And we're going to talk about something similar to the validation and cross-validation slides that we talked about before. This is assessing how good of a predictive model our logistic regression model is. And we're going to talk about something called receiver operating characteristic curves, ROC curves. The ROC should actually go here. It's receiver operating characteristic curves. So logistic regression can predict the probability that a response takes on the value of 1. And we can use the predicted probabilities that we get out of logistic regression to classify our observations or to classify future observations. So for example, if we use, and I'm going to call the cutoff value pi sub 0. So if we use pi sub 0 equals 0.5 as the cutoff, and we look at our predicted probabilities of our logistic regression model, if we see a predicted probability that's bigger than 0.5, say it's 0.6, then we would expect, or a better word here might be predict, the observed value of y to be a 1, since p hat is above the cutoff. If the predicted probability was 0.45, if we're using a cutoff of 0.5 again, then we would expect, or again a better word would be predict, the observed y value to be 0, since p hat is below the cutoff. So you see, we're just going to categorize observation based on whether their p hat is above some cutoff or below some cutoff. So this is how we're going to use logistic regression as a classifier. Based on certain observed x values, do we predict that y is 0 or 1? So it's pretty straightforward. So we're going to test how well our model classifies using a data set when the y values are actually observed. So for logistic regression, we're going to create a 2x2 classification table of predicted values from the model against the true values y equals 0 or y equals 1. So we're going to have a table of y hat equals 0 or 1 versus y equals 0 or 1. We're going to use the Donner Party data again. And remember that y equals 1 if the member survived, y equals 0 if the member died. And we're going to predict y hat equals 1. That is, we're predicting whether the party member survived. And we're going to look at several different cutoffs, several different pi zeros. And if our predicted probability is less than our cutoff pi 0, we're going to predict that y hat equals 0. That is, the member of the Donner Party died. Now again, for our data set, we know the truth, okay? And we're going to use their predicted probabilities to predict whether they lived or died. So the most common value for this cutoff is 0.5. So if we have a value bigger than 0.5, we say they lived or they survived. If it's less than 0.5, we say they died. You can do this in SAS. So here's a table I generated in SAS using ProcFreak. I'm going to show you how I did this. Here are the Donner Party data. Let me just make this so you can see the whole program here. So here are the Donner Party data. You've seen these before. And if we want to look at the table that I created, we can use ProcFreak. Well, actually, so I'm going to run my model here, and here's the output data set that you've seen before, right, where I'm going to output to a new data set called predict. I'm going to output the predicted values. And let's just quickly look at that. Proc print data equals predict. That's my new data set name that I've just created. And you can see, here's the data set with all the people from the Donner Party in it, all the other variables that are in that data set, plus then we have this new variable, which is their predicted probability. You've probably seen these before. And I'm going to start off by saying if a person's predicted probability is greater than 0.5, then I'm going to predict that they survived. And here you can see this first person actually died, but they have a predicted probability greater than 0.5. And I'm fitting a fairly simple model here, by the way. I'm only fitting age in the model to start with. I'm just having age as the explanatory variable. So this next person survived, and their predicted probability is less than 0.5. So these first two, you can see we actually got wrong. Okay. So we can create the table there that I had in the notes by, I'm just going to manipulate this data set a little bit. I'm going to bring the data set in, predict. I'm going to create a new variable. If pred is bigger than 0.5, then predicted equals 1. I'm predicting that they survived. Else, if pred is less than 0.5, then predicted is equal to 0. And then I can use proc_freq to present a 2x2 tabulation of the predicted versus the actual survival. So that's what I'm going to do here. And here you'll see, you can ignore these percentages down here for now, but the counts within the actual survival, whether they died, and then what their predicted value is. So 15 people actually did die and were predicted to have died using my cutoff of 0.5, whereas 10 people died but were predicted to have survived using my cutoff. So that's how I can generate that table. So just to summarize this for you, in proc logistic, I'm going to create the output data set. Output out equals pred, and P, what did I call it again? Sorry. Oh, data output is predict. You can call it whatever you want, of course, and P equals pred. I'm just going to call them both pred, the output data set and the predicted values, predicted probabilities. Okay. And then I'm going to say if pred is greater than 0.5, then predicted equals 1, else predicted equals 0. So that's how I'm generating my predicted survived or died. And that's how I get this table. Okay. Now, I'm going to rewrite this table, and I'm actually going to flip the two rows and columns here. In the top here, I'm going to put the truth, or survival observed. We actually observe this in the data set, so we know this is true. Okay, y is equal to 0, that means they died. Y is equal to 1 means they survived. And then, over here, I want to do the predicted condition. And this is based on, I'm predicting it based on pi 0 equals 0.5, which basically means if their predicted probability is greater than 0.5, we're going to predict y hat equals 1. If it's less than 0.5, we're going to predict y hat equals 0. And then I'm just going to move these values over here. So 0, 0, there were 15 of those. How many actually died that were predicted to survive? There were 10 of those, so 25 total. How many survived and actually died? There were 9 of those. How many survived and actually survived? There were 11 of those, so there were 20 total. Okay. So that's my 2x2 table. Notice from this that 26 out of 45 were predicted correctly. So not great. Okay. Now I'm going to introduce two words to you that you may have seen before in talking about these 2x2 tables. The first is one that I'm going to call sensitivity. And it's defined as the probability of predicting y equals 1, so predicting the person will survive. I'll say predicting y hat equals 1, when that is true. That is, when y actually does equal 1. So what's the probability of predicting that y equals 1 when y hat equals 1? This is also called the true positive rate, and from our table, you can see that it's 9/20. And we'll come back and talk about this in a second. We'll relate it to our actual data momentarily here. But the other side of this is called specificity. And that's defined as the probability of predicting y hat equals 0 when, in fact, y is equal to 0. Okay? Predicting that somebody is going to die when, in fact, they died. This is called the true negative rate. And finally, the flip side of that, the inverse of the specificity, is called the false positive rate, or FPR. And that's if we predict that the person survives when in fact they die. And as you notice, that false positive rate is 1 minus specificity. So if I write out, I'm just going to create another generic 2 by 2 table over here. And on top here we have the truth, it's either 0 or 1. And over here we have predicted, and it's either 0 or 1. If I call this A, and this B, and this cell C, and this cell D, then sensitivity, we're looking in this column, and it would actually be D over C plus D is our sensitivity. Specificity, now we're going to look in this column because we're assuming that, in fact, the person died for specificity. And that would be A over A plus B. Finally, the false positive rate is just 1 minus specificity, so that's going to be B over A plus B. That's this cell over A plus B. So, calculate the true positive rate, the negative or the true negative rate, and the false positive rate for the table for the Donner Party. So the true positive rate for the Donner Party is, among those who actually did survive, 11 out of 20 were predicted to have survived. So the true positive rate is 11 out of 20, which, if you calculate what that is, simplify that, it's 0.55. The true negative rate, so among those who actually died, how many were predicted to have died? The true negative rate is focused on this column, and 15 out of 25 were predicted to have died, or actually died and were predicted to have died. So that's 60%. So finally, the false positive rate is just 1 minus the true negative rate, so that would be 0.40, or you can also calculate it as this cell, 10 divided by 25 is 40%. Okay. So now let's think about a new cutoff. So first we used a cutoff of 0.5. But now let's use a new cutoff. Let's consider a cutoff of 0 instead of 0.5. And what does that mean? Think about that for a second. If we use a cutoff of 0, and if we say any predicted probabilities that are greater than 0, we're going to predict our survivals. And any predicted probabilities that are less than 0, we're going to predict as deaths. Well, probabilities can't be less than 0. So if we use pi 0 equals 0, we would predict that all would survive. So you can probably already see that this probably isn't a great cutoff to use. But if we use this to classify our Donner Party, I'm going to put the truth in the columns again. And the truth again are the observed values. Did they really die or did they really survive? And the predicteds, I'm going to put again in the rows. Now, if we look at the predicted probabilities again, let's just look at those. And we can look at these by just printing this data set. Again, note that all the predicted probabilities are greater than 0 and less than 1, as you would expect the probability to be. Okay? So, what's that mean for us? That means that none of our predictions will be 0. And we had 25 observations, 25 people in our data set who died. So 25 will be died, but actually will be predicted to survive using this cutoff. And 20 who actually survived will be predicted to survive using this cutoff. You might wonder why we're using this silly cutoff, but you'll see in a second. So the true positive rate then is 20 out of 20, or 1. The true negative rate is 0 out of 25, or 0. So the false positive rate is 1 minus the true negative rate, or 25 out of 25, which is 1. So let's do another silly example, and there's a reason we're doing these. Let's go to the other side of the coin here and say, let's assume that pi 0 is 1. So if my predicted probability is greater than 1, I'll predict they survive. If it's less than 1, I'll predict that they died. Okay? So again, truth or observed will be in our columns here, and the predicted values will be in the rows. And if we use pi 0 equals 1, then we would predict that they all died. Right? Because pi 0 is our cutoff, and if we get a predicted probability greater than 1, we'd say they survived. If it's less than 1, we'd say they died. Well, all probabilities are less than 1. And so now we're not going to predict that any survive, and the 25 will go up here, and the 20 will go up here. Right? Of 25 people, we're going to predict that they all died. Of 25 people who actually survived, or 20 people who actually survived, we're going to predict that they all died too. So again, so now the true positive rate is 0 out of 20, or 0. The true negative rate is 25 out of 25, or 1. And the false negative rate is going to be 0 out of 25, or 0. Okay. So why'd we do that? Well, before I tell you why we do that, let's shift gears a little bit. If we use 0.5, 0.5 is the most obvious cutoff, but it's not always the best cutoff. What we want to do is find the cutoff. We want to find the cutoff for classifying observations that would minimize error rates, that would minimize the false positive rates and also false negative rates. Okay? So sometimes we might find other cutoffs that are better. So we might want to consider all possible values of pi 0 that we might consider. And one way to do that, or the best way to do that, is to use this thing called a receiver operating characteristic curve, or ROC curve. And again, it's a technique for summarizing the classifier performance over a range of trade-offs or cutoffs between true positive rate and false positive rate. What we're going to do is the ROC curve is a plot of the sensitivity, or the true positive rate, versus the false positive rate for all possible cutoff classification probabilities pi 0. All right. The ROC curve is more informative than the classification table that we just looked at, since we're going to look at the predictive power for all possible values of the cutoff that we might use. So here are some pictures of some ROC curves. Note that on the x-axis we have the false positive rate, which again is 1 minus specificity. And on the y-axis we have the true positive rate, which is also called the sensitivity. Okay. And since these are both probabilities, the values of both the x-axis and the y-axis go between 0 and 1. So this is what we call a unit square. So what's the total area of a unit square? It's 1 times 1, or 1, right? So if we select, we already saw this in the table above, so this is really what we saw in number 2 on the previous page. If we select a low value for pi 0, then nearly all true positive values will be predicted to be positive. So the true positive rate will be near 1, will be approximately 1. But at the same time, almost all the negative values will also be classified as positive, so the false positive rate will also be close to 1. So pi 0 equals 0 is actually this upper cutoff. Okay? Or it's this upper point. Is pi 0 equals 0. As pi 0 increases, the false positive rate will decrease faster than the true positive rate. So 0 to 1, this is my pi 0, right, related to this receiver operating characteristic curve. Pi 0 is at the far right of the curve. 1 is at the far left of the curve. So it's a little counterintuitive because it's backwards from what our axis says. So the value over here is pi equals 0. The value over here in this point, where pi 0 approaches 1, nearly all the observations will be classified as negative, as you saw in the previous table. As a result, both the true positive rate and the false positive rate will approach 0. So if pi 0 equals 1, then these things will both be 0. And this is actually from number 3 on the previous page. So it takes a little time to wrap your head around what these receiver operating characteristic curves are looking at. But so as pi 0 increases, as our cutoff value increases, the FPR will decrease faster than the TPR. The false positive rate will decrease faster than the true positive rate. In fact, at least initially, the false positive rate will decrease without true positive rate changing at all, as you'll see in many of these curves. Eventually, though, the true positive rate will also start to decrease. Now, so that's the setup for these curves. A line of random guessing is this "45-degree diagonal line." Okay, this is the line that we would get if we just randomly guessed somebody's outcome, somebody's response. And the spot on this graph where we have a perfect diagnostic technique is in this upper left-hand corner, where we have a false positive rate of 0, so we never indicate a false positive rate, and a true positive rate of 1. So we always hit all the positives and we never indicate a false positive. So this corner is what we're aiming for. Okay? So on this graph, I have 3 different ROC curves. 4 actually, if you count the random guessing one. So random guessing means we just flip a coin to decide whether somebody is going to be going to survive or die. Okay? This first curve, I'll just trace it here quickly, which is close to the random guessing line. This is actually a pretty bad model. This is an indication of a bad model. It's really little better than guessing or than flipping a coin. Okay. This top curve, you can see it goes all the way up here into the upper left corner. This curve is almost perfect. It's an almost perfect model, because our target is that upper left-hand corner, and that purple curve gets us almost to that point. That's a little bit unrealistic. We don't often see that. But what we do often see is something that's more like this middle curve. And that is actually a good model. Okay. So we'd like to see the purple curve, but we don't often see that. But what we often see is something hopefully like the blue curve. And we want to stay away from things that look like the green curve. Okay, so that's the setup for ROC curves. And I think what I'll do is pause this.